Hi, I am Ambrozio, and this is my contribution to the first Geometric Analysis Festival, organized by Hojo Lee from the Jeonbuk National University in South Korea. The title of my talk is Systolic and Diastolic Invariants Related to Minimal Surfaces. This is video number 3, and the plan is to discuss the diastoles of Riemannian spheres. Let S3 denote the unit sphere centered at the origin in R4. S3 is very simple from the topological point of view, in some sense. So closed curves and surfaces are all null homotopic in S3. However, there is no trivial topology on the space of embedded topological two spheres inside S3. In order to convince you of that, let me discuss this family here of two spheres, which you obtain by intersecting S3 with horizontal hyperplanes in R4. So there should be a picture here, a picture that I would draw during the recording of the video. However, it did not quite work, so I will ask you to use your imagination. So you have to picture the sphere in R3, the unit sphere in R3, and you have to picture the family of embedded two spheres, which are the intersection of S3 with horizontal hyperplanes. Okay, so I want to convince you that this family, which is a continuous family of embedded two spheres, should be regarded as a non-trivial loop in the space of embedded two spheres in S3. So first of all, let's see why it is a loop. And here we need to make an identification, right? Where we need to think that the intersection of S3 with the plane at height -1, so this gives us just the south pole, right? So this you can think as a trivial two-dimensional sphere. And likewise, the intersection of S3 with the hyperplane at height t equals 1 is the north pole, so this also think as the trivial two sphere. So this family of two spheres, or of horizontal two spheres, you can think of it as a family that starts at the trivial two spheres and ends at the trivial two spheres. Okay, so we have a loop, a closed loop. It starts at the trivial two sphere and ends at the trivial two sphere. And why do I say that it is a non-trivial loop? Well, the reason is the following. So as we move along the family, as we move up from the south pole to the north pole, passing through the equator along the family, we can keep track of what is below each one of the horizontal two spheres. And if we do that, we see that something topologically non-trivial is happening. Why? Because at the beginning there is nothing or very little below the two spheres in the family. But at the end, or almost at the end, what we see below the two spheres of the family is almost everything, and eventually everything, right? So the end point from this point of view looks very different to the initial point, and that's why I say that this is a non-trivial loop in the space of embedded two spheres in S3. Okay, out of this single non-trivial loop, we can construct several other non-trivial loops. When we can do this, for example, by using this procedure, we can take a continuous family of diffeomorphisms of S3, each one isotopic to the identity, and then we can define a new family whose T slice is the surface sigma T, which is the image by the diffeomorphism phi of T of the horizontal sphere sigma bar T at height T. Okay, so let's see what happens. So the diffeomorphism of the family are possibly vary, but they are all continuous. So I don't know, the south pole can be sent to another point. The spheres that are near the south pole will be sent in a strange way. They are all varying, but eventually they close up in a single point. That is the image of the north pole by phi of 1. Okay, and by the same reason that I explained, we can understand this phi sigma of T as a non-trivial loop in the space of embedded two spheres. A non-trivial loop that is somehow homotopic to the initial non-trivial loop of horizontal spheres. Okay, just to give a name to those objects, I will call the family sigma bar T the standard sweep out, and all those other families obtained by this precise procedure that I have just described we'll call admissible sweep outs. Okay, now I will introduce a Riemannian metric and start doing some measurements. So for each admissible family, I will compute the maximum of the area of the two spheres in this family, and then I will take the infimum over all admissible families. Okay, if I do this computation with respect to the metric G, the number I get is what I will call in this talk the diastole of S3 with respect to the metric G. This invariant is non-trivial, so here I want to spend a bit of time explaining why is that, because the argument is actually quite pretty. So by construction and that observation that I said about what lies below each one of those two spheres, we see that whatever admissible family we are looking at, there is one slice, at least, which divides S3 into two pieces of the same volume. Okay, because at the beginning there is little below, at the end there is everything below. So by continuity in the middle, there is some slice which divides S3 into two pieces with the same volume. And this is the situation. This situation, right? So is related to the isoperimetric problem. Recall that on any closed Riemannian manifold, there is a positive lower bound for the area of any hypersurface that divides the given Riemann manifold into two pieces of the same volume. Okay, so this is known as the isoperimetric inequality. And so we can apply this fact here to conclude that this maximum area for all families will be at least as big as this isoperimetric number, right? Because all families will have some surface that divides S3 into two pieces of the same volume. Very good. So actually, using this isoperimetric idea, I will leave you another exercise, which is to compute the diastole of S3 with the canonical metric. And as you will see, the answer is 4 pi, which is the area of the equator. Okay, so let's make another remark, which is that this number that I have just defined, the diastole of S3 with respect to the metric G, is well, the most common name you will see for it is the Simon-Smith min-max width of S3 with respect to G. And this is because well, this number was defined by Simon-Smith back in the 80s when they were trying to implement a min-max procedure that would find a minimal two-dimensional sphere into S3. And actually, from the point of view of Moss theory of the area functional on the space of embedded S2s in S3, this number, the diastole, should correspond to a Monton-Pires critical level. Okay, so at the critical level you find critical points. Critical points are of the area functional are minimal surfaces, right? So that's why they were thinking about this number, and they managed to complete the problem, and they proved the following theorem, which I will call the min-max theorem. So they showed that for every Riemann metric on S3, there exists a collection of mutually disjoint embedded minimal two spheres in S3G, and a collection of positive integers such that the area, well, the diastole of S3G is equal to the sum of the areas of those minimal two spheres counted with multiplicity, with integer multiplicity. Okay, so in particular, right, so there exists on every Riemann three-dimensional sphere at least one embedded minimal two sphere. Okay, there is a complement to this theorem, which is also a confirmation, right? So of an idea or a principle in Moss theory, right? So from the point of view of the type of the critical point you produce by such Monton-Pires procedure, what you expect that is that the critical point you produce will have an index of instability bounded from above by the number of parameters of your Monton-Pires argument. And in this case we are doing a one parameter Monton-Pires argument, and what we expect is a index bound by 1. And well, Marx and Neves in the last decade they they showed that, they confirmed this, they showed that in the previous statement, in the min-max theorem, you can find the minimal spheres in that statement in such a way that the sum of the Morse index is at most 1. And another information that I want to give you is that if one assumes extra geometric conditions, then the statement becomes even more transparent. Okay, so Marx and Evans also into the 2010s, they showed that if the Riemann metric on S3 has positive Ricci curvature or is homogeneous, then you can find a single embedded minimal sphere with Morse index equal to 1 and area equals to the diastole. Right, so this sigma here, if it's not clear, should be a sphere like in the two-dimensional sphere like in the previous statements. Okay, so positive Ricci or homogeneity are situations where the diastole is realized as the area of a single embedded minimal to a sphere with Morse index equal to 1. Now comes the problem that we have been proposing about our geometric invariants related to minimal surfaces. So what happens to the diastole of S3G as the metric G changes? We want to compare it to the volume, and the precise problem we want to study is to understand how the diastole of S3 divided by the volume of S3 to the power 2 over 3, how this quotient varies as the metric G varies. Okay, so if you think about very long and thin ellipsoids, but with fixed cross section, it's not difficult to argue that the diastole, the normalized diastole by the volume, can be made arbitrarily small. So, as in the second talk about systoles, the problem here is to investigate how big this normalized diastole can be as the metric G varies. Okay, so let me start with a positive result. So in 1985, Treibergs proved an upper bound for the normalized diastole of metrics that are very special. So let me read the statement precisely. So assume the S3 that we are looking at is the boundary of a compact regular convex domain in the Euclidean space R4. So this boundary comes with induced metric, and what Treibergs tells us is that with respect to this metric, the normalized diastole of this sphere is at most a constant C that is, well, universal, doesn't depend on omega or anything else. Treibergs' argument was very nice actually. So because how did he prove? How did he find this upper bound? Well, what he did was to he used the definition actually, right? So he, in other words, he showed that it's always possible to find a sweep out of such S3s in such a way that they have area controlled by the volume of the given S3. And how did he do that? So he considered the natural class of sweep outs that the problem suggests, right? So our three-dimensional sphere is inside R4, and likewise we did for the unit sphere, we can sweep it out by intersecting it with parallel hyperplanes, right? So and these were the sweep outs that he tried to estimate, and he did the nice trick of averaging, right? So basically he showed that the maximum slice of such sweep outs by parallel planes on average is at most a constant c times the volume to 2 divided by 3, right? And that gives you the estimate for the diastole, normalized by the volume. Okay, so this is Treibergs' theorem. A few years later, Croke improved the constant. So I did not say this explicitly, but from my description you can guess that the number c that Treibergs found was explicit. And Croke gave a better estimate for c using different ideas. And well, I think it is still an open problem, actually a nice open problem in convex geometry, to find what the sharp constant is. Okay. Okay, so let me say this. One thing that is known is that the sharp constant is not the constant that you get by plugging the canonical metric. So actually it is known that there are other shapes that have bigger diastolic normalized diastoles. Okay. Okay. Anyway, this is the equation, the open question that Treibergs' theorem leaves. Now let me show you a negative result, right? So by a construction of Burago, Ivanov, and Guth, one can say that there is no universal bound that holds for all Riemann metrics on S3. And so we checked this as well, but we checked this explicitly. So we showed that there are no universal bounds for the normalized diastole of three-dimensional Riemannian spheres by taking the family of Berger spheres with collapsing Hopf fiber and checking that for this explicit concrete family of homogeneous metrics with positive curvature, the diastolic normalized diastole is converting to plus infinity. Okay, so with Rafael Montezuma, we produced an explicit example displaying some interesting geometry. Okay, and as you can imagine from watching video number 2, it was by knowing that diastoles of homogeneous metrics are realized as the area of minimal two spheres inside S3 that we could do the computation and check this result. Okay, so we have seen a class of metrics for which there is an upper bound for the normalized diastole, right? Namely, the class of boundaries of convex domains in R4. And we have seen another class of very nice metrics, homogeneous metrics with positive curvature, for which the supremum of the normalized diastole is plus infinity. Are there other interesting classes of metrics to look at and to try to prove upper bounds for the normalized diastole? And together with Rafael Montezuma, we answered to this with an yes. Let me start by remarking that the canonical metric is such that its normalized diastole is equal to the cubic root of 16 over pi, and we show that this number is an upper bound for the normalized diastoles of metrics that are nearby the round metric inside its conformal class. So let me be very precise and state the full theorem that I proved with Rafael Montezuma. So assume G is a Riemann metric in the conformal class of the canonical metric G1 that has positive Ricci curvature. Then the normalized diastole of such metric on S3 is at most equal to the cubic root of 16 divided by pi. Moreover, equality holds if and only if G is a metric with constant positive sectional curvature. Okay, so this is a sharp isodiastolic inequality for metrics in an open neighborhood of the round metric inside the conformal class of the round metric, which is a sharp estimate. Okay, the equality case characterize the round metrics. Okay, so let me give you two ingredients of the proof of this result. So the first ingredient is the normalized Yamabe flow. I wrote the formula. So this is a geometric flow. R here is the scalar curvature, and normalized means that this flow keeps the volume fixed. And notice that this flow happens inside a conformal class. So we use the normalized Yamabe flow to connect our metric, like in the theorem, to a metric with constant sectional curvature. And we studied how the diastole is changing along the flow. Okay, so this is one ingredient, and here is where the assumption of positive Ricci enters somehow. So it is known that such Yamabe flow starting at a conformally flat metric with positive Ricci will continue forever with positive Ricci and converge to a constant sectional curvature metric. So here we use this preservation of positive Ricci, and that helped a lot in the study of how the diastole changes along the flow. Because remember, in positive Ricci, the diastole is realized as the area of a single minimal geosphere of index 1. And index 1 enters here, so the second ingredient is a sharp estimate that holds for index 1 minimal spheres in Riemannian 3 manifolds. So the integral of the ambient scalar curvature over such index 1 minimal sphere is at most 24 pi. And this estimate is sharp, so if you notice, in the case of the canonical metric, the equator is a minimal sphere with area 4 pi, and the canonical metric has constant scalar curvature 6. So this inequality is somehow sharp. And well, these are the two ingredients. Maybe I will leave the discussion about how they appear in the proof to the Q&A session. And now I want to move on. Okay, so let me pose a few further questions about the diastoles of S3. I think it would be very interesting to know about homogeneous metrics. And unfortunately, our methods, well, we could not use the methods to say anything about other homogeneous metrics. So the method is somehow very tight, so everything is very sharp, so unless we can refine a few things, maybe item B, it's unclear how to use our argument to, well, how to generalize our argument in the case of other homogeneous metrics. But anyway, another, well, negative aspect of our theorem is that is the restriction on metrics with positive reaching, right? So I don't know if one can remove that hypothesis. So it is theorem does not answer really whether there are conformal classes of metrics on which this supremum here is finite. But anyway, we do have Treibergs theorem, we do have our theorem, so they are suggesting that there may be interesting subsets of metrics for which this supremum is finite. And if this is the case, then it's interesting to understand whether this supremum is attained or not. Maybe it's attained, but not by a Riemannian metric, or maybe it's not attained, so we don't, well, a priori we don't know, and this is something that I think is interesting to be understood. And finally, if this supremum is attained, then one can ask, how does a maximizing metric look like? Okay, so regarding this last question, Raphael and I proved a certain necessary condition. So a maximizing metric will have a very large set of minimal two spheres. Actually, they will be all over the place. They will be equidistributed in a very precise measure theoretical sense. Anyway, so maybe this is another point that I will leave to the Q&A session. Right, so let me now discuss a bit about the diastole of two spheres. So you probably have noticed that I started talking about 3 dimensions instead of talking about 2 dimensions. I did that because the relevant min-max theorems are much neater to state in the case of the 3-dimensional sphere. So there are similar diastolic invariants related to closed geodesics in Riemannian two-dimensional spheres. But there are different ways to implement it, right? So, and even the ones allowing more sweep outs or a bigger class of sweep outs, so they may produce either closed simple geodesics or figure 8 geodesics, whose length attains the value of the diastolic invariant. Okay, so we have a notion of diastole. It is realized, but it's realized not by a closed simple geodesic necessarily. It could be a geodesic with self-intersection. But that's not all bad. And by estimating the maximum length of sweep outs and using these what I just said, Croke showed a diastolic inequality. So he showed that any Riemannian two sphere with area 1, say, contains a closed geodesic with length at most this number 31. So you have to think here of this closed geodesic as being the geodesic that realized the diastolic invariant. Okay, the constant has been improved over the years by many authors, and if I'm not mistaken, the best constant so far was obtained by Regina Hotman, and so she proved the bound 4 times square root of 2. And it's still not know what the sharp constant is. So the conjecture, known as the Calabi-Croke conjecture, is that the supremum of this normalized diastole of two spheres by the square root of the area is at most this number, square root of 2 times square root of 3. This conjecture is open even for metrics with positive Gaussian curvatures. Right? So in the situation of Treibergs statement, we still don't know the best upper bound. But we do know this estimate by Croke, which is twice the number that he conjectured. And what is this number? So this number is the diastolic, the normalized diastole of a very special singular metric on S2. So you have to picture an equilateral triangle, two copies of an equilateral triangle with the flat metric, the Euclidean metric, and then you glue them on top of each other. And this is a metric on S2, which is flat almost everywhere except at the 3 tips on which you see conical singularities. If you study the diastole of such singular object, you see that it is a certain number that if you divide it by twice the area of the equilateral triangle, what you get is precisely square root of 2 times square root of 3. So without making a picture is a bit difficult to explain, but if you are using your imagination, you can imagine that what is the diastole, right? So you have to imagine, say, the height of the equilateral triangle. So it will go to the basis of the equilateral triangle, but then it will go back by the second equilateral triangle. So this will give you a closed geodesic passing through the tip, and this is and there is a sweep out where this guy is the sweep out with maximum length, and there is no other sweep out with less less. Okay. Yeah, so this will be also a good topic for the Q&A session. Sorry. Okay, so this I think is the last thing that I wanted to say about the diastole of two-dimensional spheres. And just to finish, I want to make a comment for those that are more used to the several min-max theories for the error function. So the Simon-Smith min-max procedure is a procedure, well, in the case of the tree-sphere, that restrict the topology of the slices of the sweep out, right? So we were sweeping out S3 by two-dimensional spheres. But there are other theories that allow more other topologies and also more general objects that embedded two spheres. And the more sweep outs you allow, right? So if you think about the definition of the diastole that I gave, the more sweep outs you allow, the smallest will be the diastole, the min-max number that is associated to your min-max procedure. And so since the Almgren-Pitts theory is the one that looks, for me at least, who am not a specialist, it looks like the one that is the most flexible. It allows sweep outs that are fairly easy to deal with. Well, because you can cut and paste and, well, anyway, just to summarize, I would argue that the Almgren-Pitts theory is the one that gives you the most appropriate notion of diastole in the case of arbitrary Riemannian manifolds of all dimensions. And thinking about keeping in thinking about codimensional one objects, there is also strong indication that this should be the interesting notion of diastole to think about when comparing to the volume. And this is a result by Glyn-Addy and Yukomovich. And they showed that for this notion of Almgren-Pitts diastole, there is on each conformal class an upper bound for the normalized diastole by the volume. Okay? And this is in strike resemblance with what with the sort of the kind of question that you ask about the first Laplace eigenvalue. So it would be really amazing if one could establish analogous theory for the Almgren-Pitts with compared to the volume, making the analogy with the first Laplace eigenvalue compared to the volume. That would be really amazing to answer the question of what are the sharp constant, etc., depending on the surface, depending on the conformal class. All this would be, I think, amazing to know. And the very last comment that I want to make, also thinking about why I think also posing a problem around what I just said about the suitability of the Almgren-Pitts being max to as a notion of diastole, is this result of Glyn-Addy and Yukomovich, which was proved independently by Saburo. So they show that for Riemannian manifolds of dimension n and positive Ricci curvature, there is a universal constant bounding from above the normalized Almgren-Pitts diastole by the right power of the volume. Okay, and you see, this is not a contradiction with my computation with Raphael of the Simon-Smith diastole, this is not a contradiction, because what I said, the Almgren-Pitts allows more sweep-outs, and it is a known fact that for Berger spheres, Berger metrics with small parameter rho, with fibers that are very small, the Almgren-Pitts diastole is smaller than the Simon-Smith diastole. So, right, and this is, I mean, it's because you allow more sweep-outs, so this number is smaller than this, and in the end, you do get an upper bound for the normalized Almgren-Pitts diastole among metrics with positive ridge curvature. And well, I think all that suggests similar questions. So what are the sharp upper bounds? What are the sharp constants? What are the metrics that realize the sharp constant, if there is one, etc., etc. And I think this is the end of my third talk, and thank you very much for your attention, and see you in the Q&A session.